Welcome one, welcome all. And today I'm going to be talking about my favorite, probably my favorite thing to talk about in astrophysics or astronomy is black holes. I think they're one of the most interesting things that I've ever learned about or tried to study on my own. But black holes. So let's get straight into it. First, what is a black hole? Black hole is an object that has collapsed under its own gravity into an infinitely small point, known as a singularity, with infinite density. As you can see, for people that are watching on YouTube, this is just an artist rendition of a black hole. We talk about black holes in the astro community, but people outside of the astro community, they don't really know what a black hole is or how they form. And that's what I'm going to try to tackle or teach you today. But before getting into the details of how things become black holes, I'm just going to go over the basic types of black holes. There are really two main types: stellar, supermassive. Intermediate is also another type, and then there's miniature. I'm going to go over the first three: stellar, intermediate, and supermassive. But those are the three types of black holes. As you can probably tell by their names, stellars form from stars, intermediate are medium-sized stars, and supermassive are supermassive black holes. They're not intermediate stars, but intermediate black holes, and then the supermassive black holes. And miniature, I'm not going to go into miniature because it gets very, very complex because some miniature black holes are made in labs and stuff like that. So I'm not going to get into that. Just going to go over the three basic types of black holes. Stellar black holes are generally formed from dying stars, the collapse of their cores. I'll get into that a little bit later. They can range anywhere from 5 to 100 solar masses. And what solar masses means is how many, one solar mass is the size of our sun. So 5 solar mass star is something that's 5 times bigger than our sun, to put in perspective for people that are not in the astro community. So they seem, even though these are the smaller of the three, they can still be massive in terms of 100 times the mass of our star. So if a star is big enough, the core will collapse to a black hole to when gravity is greater than the radiation pressure. And the biggest factor is, or one of the biggest factors is the Schwarzschilds Radius. I apologize if I'm butchering that. And again, I'm going to go in depth of that a little bit later, but just mentioning that right now. Next, we have intermediate black holes. These range from 100 to 1,000 solar masses. Intermediate black holes are bigger than stellar black holes, but they don't generally form from a single star, the collapse of a single core. So some ways the intermediate black holes are formed is the merging of two stellar mass black holes over basically two stellar black holes merge together, and they can become a intermediate black hole. If you could imagine a let's say a stellar black hole that's 50 solar masses, and you have another stellar black hole that's 50 solar masses. They merge together, there are 100 solar masses. Now you're talking intermediate black hole. Or they could also be formed by a stellar mass black hole that accretes mass over time. And as it accretes mass, it gets bigger and bigger and bigger, and it could enter the intermediate black hole range. Another way is the collision of massive stars in dense stellar clusters and the collapse of the collision. So basically the same concept of merging black holes, but instead of merging black holes, you have two big stars that merge together. And because of that, the mass of the two stars merging will collapse all the mass will collapse to a black hole. And another idea is that they're primordial black holes, which means they were formed during the Big Bang. I'll get into that theory on the next slide with the supermassive black holes. So supermassive black holes can range anywhere from, that's supposed to be 100,000 to billions of solar masses. So billions of times bigger than the mass of our sun. They are, like their name suggests, they are super massive. The origins, there's uncertainty of the origins of supermassive black holes. There are three main ideas. One is intermediate black holes that accrete mass over time. It's very similar to how intermediates form from stellar black holes accreting mass over time. You have intermediate black holes that accrete mass over time, eventually get in that range of supermassive, or you can have two intermediate black holes that merge together to create a supermassive, and again, formed early in the universe through the collapse of supermassive stars. So in the early times of the universe, before the universe was 14 billion light years, across, or 14 billion light years big, the distribution of the mass of the universe wasn't as spread out as it is now. That it was a more dense universe. Things were closer together. So it's believed that in the early years, the early times of the universe, that majority of the stars were massive stars, supermassive stars. And so if you have a supermassive stars, stars that are 100,000 solar masses, they can collapse into supermassive black holes. And so it's the idea, if you think about the idea that, because let's say you have a supermassive star early in the universe, when that star explodes, the material from that star can be used to create multiple stars from that initial star, but they would be smaller. It's the same concept. So in the early years, there were bigger, more massive stars. Therefore, there were supermassive black holes would probably be more common. This is just an idea. So now we're going to get into the three main layers, or three main, I don't want to say structures, three main layers of a black hole. You have the outer event horizon, which are just the areas outside the event horizon, the inner event horizon, things that are inside the event horizon, and the singularity. And we'll get into what the singularity is in a minute. So here's some structures of a black hole. So singularity, which is this small finite point, which is basically where the mass is at in a black hole. It's in the center of if you're looking face on at a black hole, it's the dead center of a black hole. And it's an infinitely small point in space with a discrete mass and an infinite density. The event horizon is a theoretical boundary around a black hole where nothing can escape. The photosphere is a region of space where the gravity is so strong that photons are forced to travel in orbits. So literally light, when it gets to the photosphere, light itself will orbit a black hole. The innermost stable orbit is the radius where the last stable circular orbit can exist. Anything inside of this radius will fall into the black hole or be pulled into the black hole. Accretion disk is the circular elliptical structure that's formed when material falls towards the black hole. So again, it's accreting mass. All this mass is just falling in or being absorbed by the black hole. And relativistic jets is when you have an accretion disk, but the black hole is spinning. So the accretion disk is strongly magnetized. If you look up a picture of this, it looks like lasers are coming out of the black hole. So now let's get into how things become black holes. So we're going to take an example of a white dwarf. A white dwarf is a very old, mature, you can imagine it as like an elderly star. It's a star that's basically dying off. There's many ways it can become a white dwarf, but let's just say we have a white dwarf. It used to be a red giant and it had shed its mass. We have a white dwarf. So there's a concept of degeneracy. Degeneracy, to put simply, I'm going to simplify a lot of these terms, but degeneracy is basically when atoms in a star have been compressed to the point where the star can no longer get smaller. For my non-astro minded people, imagine you have a balloon full of Skittles, right? You put Skittles in a balloon and you blow the balloon up really, really big. When it's really, really big and you shake the balloon around, the Skittles are going to bounce around. They got a lot of space to move. It's a lot of Skittles just going everywhere. Well, if you start to slowly let air out of the balloon, and let's say you have a good amount of Skittles in there, eventually the balloon will get to a point where all the Skittles are balled up together, and the Skittles have been compressed to the point that the balloon can't get any smaller. At that point, it's just a sack of Skittles inside of a balloon. Same kind of concept, but with just atoms inside of a white dwarf star. So this brings us to hydrostatic equilibrium. And again, I'm simplifying this stuff for you guys, but that's basically when the degeneracy pressure, which is outward pressure, is equal to the gravity due to its mass, which is inward pressure. So gravity is pulling in, The fact that it's degenerate means it can't be compressed anymore. So that pressure is pushing out, and you have a star that's in equilibrium, that's not getting smaller, that's not getting bigger. It's just static, right? It just stays the size it is. And that's what that's what white dwarfs are. They're in hydrostatic equilibrium. And that's why they just stay the size they are. Now, where black holes come into play is when gravity gets bigger, the force of gravity inward is stronger or overtakes the degeneracy pressure. It's when you collapse into a black hole. There are multiple ways for a white dwarf to collapse to a black hole. You might have a white dwarf that has a companion star, and it's slowly pulling in the mass from the other star. It could get big enough to where the force of gravity becomes stronger than the degeneracy pressure, and it collapses. Or if you have a star that's big enough to begin with, a star's 20, 30 solar masses, when it supernovas, the remnant core from the supernova is all big. Its mass is big enough to where it's already at the point where its mass is big enough to where the force of gravity can overtake the degeneracy pressure, and it collapses to a black hole. Many ways for this to happen, but this is just an example of how a white dwarf can become a black hole. This could also happen if you have a thick enough molecular cloud, or I'm not going to get into all that, but it mainly happens with stars. So now one of the other big factors is, like I mentioned earlier, the Schwarzschilds radius. So Schwarzschilds radius is the radius of a black hole's event horizon, or it's the radius at which an object with a discrete mass must be compressed to become a black hole. The equation is actually fairly simple. The radius is just equal to 2 times the gravitational constant, the mass of the object, divided by the speed of light squared. And every object with a mass has a Schwarzschilds radius. And so obviously the larger the mass, the larger the radius will be that you got to compress it to. So for example, a star like our sun, its Schwarzschilds radius is about 3 kilometers. So that means if you were to take our sun and compress it to 3 kilometers, press it down to 3 kilometers in radius, it will collapse into a black hole. Another example, if you take the Earth, let's say you were big enough to squeeze the Earth down, the Earth's Schwarzschilds radius is 1 inch. So if you take the Earth and compress it down into a ball that has a radius of 1 inch, it will collapse into a black hole. And last example, to put in perspective how the mass is directly proportional to the mass of an object. Let's say you take Mount Everest, I believe the biggest mountains on Earth, massive, huge. I couldn't tell you how much Mount Everest weighs, but if you were to compress it, you would have to compress it down to 1 nanometer for it to collapse to a black hole. 1 nanometer is 10 to the minus 9 meters. And for those of you guys that aren't astronomically minded, to put in perspective, the thickness of a human hair is 60,000 nanometers. 60,000 nanometers is the thickness of a single strand of human hair. You would have to compress Mount Everest down to 1/60,000, if I think that's how you say that, of that. You'd have to compress it down to 1 nanometer, which is 1/60,000th of a strand of hair, which it's small. It's very, very, very small. But that's how small you would have to compress Mount Everest down to get a black hole. So I hope you guys learned something. I hope that made sense, and the simplification of things wasn't too bland, and it wasn't too complicated for those that have no idea what black holes are. I appreciate you guys for listening, and class is dismissed.